everyone. Thanks for coming. And thank you to the previous speakers. I really enjoyed those talks. And it's going to be an interesting session, linking it all together. So I'm going to talk about, it's all quite linked, but intelligent machines that learn. What do they know? Do they know things? Let's find out. I'm actually not going to talk about much of my work, any old work, so I just want to give a bit of a background. I share this video in a lot of my talks. If you've seen it, apologies. This is kind of like a selection of work up to 2014, just to give a bit of background information as to where I come from, what my interests were, to give context to what I do now. It's also a good excuse to play Black Sabbath on a PA. So basically, I'm a computational artist. I work with computation both as a medium. Can you hear me, by the way? This is good, yeah. So I work with computation both as a medium and as a subject matter. Really, my domain is visual, so I'm a visual artist. I also work with sound a lot. But always I'm interested in emerging technology, both as, again, as a medium and as a subject matter, and its the cultural and social implications, as well as how it impacts how we create. And specifically in some of these cases, for example, how I can express myself through some of these technologies. So a lot of this stuff, well, all of this stuff is all interactive. So in these kind of works, I'm exploring how I can create interactive systems that I can kind of play like an instrument. And this goes back about a decade, some of this work. So from here, I've been getting really interested in AI. You could maybe kind of call some of this stuff that's driving this AI. This is one of the problems with AI. It's such a vague and broad term that you can bend anything to be AI. Or actually, you could shoot everything down. You can beat the world's best Go player and say, well, that's not really AI. It's just maths. So AI is a term that I'm actually not going to be talking about. Particularly, my interest is in machine learning, which is what I'm going to be talking about. So, yeah, AI. This is what it looks like. It's blue and very shiny, and it's really hot these days. It's very popular, and it should come as no surprise that it's really big right now, even though it's been around, since the 60s. This is the Google trend graph for the term AI, which is pretty flat, and slight spike in 2012 when Google AI learned about cats, and then it gets really big towards the end. And yeah, this should come as no surprise, because this is the trend graph for the term big data on Google News. So it starts around 2011, if I remember correctly, and so we have like 4 or 5 years of big data before we have this explosion in AI. And I like this as a kind of metaphorical analog for how intelligent life might have evolved as a result. In fact, this is kind of what I guess people think, that as we adapt, as we evolve more senses and we're able to receive more information from the world, we require the ability, the cognitive ability, to process that information in order to make the right decisions. So in effect, organisms, as we gathered all this new big data, we became more and more intelligent. In fact, some organisms started learning how to model the environment so that they could make predictions and react better. In fact, some organisms even went even further to model not only just the environment, but model other organisms and develop maybe a theory of mind. So I like this analog that as a result of big data, we are now developing artificial intelligence. I actually talk about this a lot. I spoke about it at the Resonate last year under the guise of a digital god for a digital culture. It would have been very appropriate for today as well. I'm not going to talk about it much because I have new things I want to say, but just to summarize the idea which I'm going to build on today is this idea that deities and our overseers have evolved along with our societies and our values. And as a society, we've lost our spiritual sensibilities and become so immersed in materialism and technological submission. Our overseers have also evolved and have lost their spiritual sensibilities and become material, technological. And of course, this is linked to the main driving force of the big revolution in AI, which is the mass surveillance. And I find it so fascinating how this relates to the ultimate panopticon, that is God. So, yeah, this is a realization I came across a few years ago, which is that all of my work is about really two things, waves and God, and kind of science links these two together. But, so I want to talk about, I said about AI, but AI is a problematic term, so I want to talk about learning, and this is what I'm really interested in. Machine learning is what I want to talk about, and potentially different modes of perception and cognition, which is what we're now at a stage where we really have to think about these things. This animal's become really popular in the last couple of years. I tweeted this just the other day because New Scientist had an article. I've seen 3 books in the last year because these things are they're really clever, but they have a weird distributed kind of intelligence. The arms are semi-autonomous. They have 2/3 of their neurons in their arms. They have the same amount of neurons as a cat. They're really, really clever, and they diverged evolutionary about 500 million years ago. So these new modes of consciousness and perception I find really interesting. So the main question that I'm interested in right now is, what does it mean to learn? What does it mean to understand? And what's the difference between learning and memorizing? How is all of this linked to perception and cognition? And so my interest in machine learning is quite varied. It's both trying to look at these philosophical questions about perception, cognition, intelligence, creativity, but then also the social, cultural impacts of this emerging technology and how it's going to affect our lives on a day-to-day basis. But also on a very practical level, again, how can I use this technology to enhance or enable artistic expression? Or in particular, I'm doing a PhD now in real-time interactive human-machine collaborative creativity. What you're seeing right now, I'm going to talk about at the end, is basically a machine learning to see, like from the beginning, not trained, to being trained. I'm going to talk about that at the end. So I want to talk a little bit about why I find the concept of learning or machine learning really, really fascinating. It's expressed by this dialogue. So this is Ada Lovelace, which maybe some of you know. She's credited as being, the world's first major computer programmer. She was 17 when she started working with Charles Babbage, who invented the big mechanical computers in the 1800s. And she's actually a lot more than just a programmer. Charles Babbage created these machines that could compute any computation. He was very, very proud of this. But he still saw it as a way of computing numbers. And it was Ada Lovelace who saw the potential of these machines to go beyond just crunching numbers. And she said it weaves algebraic patterns just as the jacquard loom weaves flowers and leaves. And one of her, really profound statements was, the engine might compose elaborate and scientific pieces of music of any degree or complexity. She wrote in 1843. She also said something that's very controversial, and still 2 centuries later, we're still arguing about it. And she said that the analytical engine, which was this machine, has no pretensions whatever to originate anything. It can do whatever we know in order it to perform. It can follow analysis, but it has no power of anticipating any analytical revelations or truths. Its province is to assist us in making available what we are already acquainted with. And this was in 1850, I think. We see this in her notes. So a century later, in his seminal 1950 essay, Alan Turing addressed this statement. He was very concerned. He opens his essay with the now famous really line, "Can machines think?" And again, 7 decades later, we're still arguing about this very question. And he refers to this objection by Ada Lovelace as the Lady Lovelace's objection. And he goes on to say that for a machine to be able to originate anything, it must be able to learn. And he had already theorized a few years before things called unorganized machines, which were machines that could learn. So they're kind of like neural networks that he proposed in 1940-something, I forgot now, and they were inspired by the neurons in the brain. So he thought that Lady Lovelace said this because she wasn't aware of machines that could learn. But if a machine could learn, then it could surprise us, and that was the essence of a machine originating something. And then he had the insight to say, instead of trying to produce a program to simulate an adult's mind, why not produce one that simulates a child's mind and then educate it? Which is basically what machine learning research today is kind of about. But of course, designing the child's mind is billions of years of evolution, which is still a problem we're trying to address. He went on to say that the important feature of a machine like this is that its teacher will be very largely ignorant of what is happening inside. And this is one of the greatest strengths and greatest dangers of machine learning, because it's because of this that we will potentially be able to really go beyond our own capability, like, cure leukemia, or even learn how to photosynthesize as a human. But also, it's obviously very undesirable potential as well. And the physicist Max Tegmark has a very nice kind of anecdote about this. He calls it the wisdom race, where, in the olden days, we would invent something like a car, and then decades later, after thousands and millions of people have died, we say, how about a seatbelt? How about an airbag? How about traction control? But as our technologies become more powerful, like nuclear tech, synthetic biology, AI, we can't afford to have that lag. We can't afford to let things go wrong before we try and fix it. And one of my favorite quotes about things going wrong and not working as intended is by Charles Babbage, 2 centuries ago, the inventor of this machine. And it's shocking to see how a lot of the mistakes that are happening right now in AI, in machine learning, is basically this. And what he says is, on 2 occasions I've been asked by members of parliament, pray Mr. Babbage, if you put into the machine wrong figures, will the right answers come out? I am not able rightly to apprehend the kind of confusion of ideas that could provoke such a question. So before I get on to my research, very quickly, what is machine learning, in case you're not familiar? It's basically about learning a function. You've got this function f, you give it an input, which is x, which could be a number, it could be an image, it could be a sound, and it outputs another set of numbers, y. But you don't write the function f. You give it loads of, to make the example simple, you give it lots of x's, lots of y's, and it figures out what that function is. And for very complex problems, like an image with millions of pixels, the way you do this is you go deep, and that's what deep learning is. And the idea here is you have lots of chained functions, and each function is learning something else. And all the functions are learning at the same time. So the first function might learn how to detect edges. The second function might learn how edges can come together to create circles. The third function might learn how circles come together to create wheels. The fourth function might learn, okay, you've got a bunch of circles there, you're probably a car. And when you pipe data, so every function has learned one thing, and every function is a very high-dimensional transformation. When you pipe data through a neural network like this, it is literally a journey through multiple dimensions and transformations in space and time, because every layer is this transformation in a dimension. Also, I want to quickly ask, does anyone know what this is an image of? It's the Crab Nebula. It was released just a few days ago. This is the kind of famous photo of the Crab Nebula from 1999. It's 11 light years across, 6,500 light years away. And this was released just a few days ago. It's a composite. It covers full spectrum, X-ray, IR, UV, etc. But the interesting thing about it is it's the remnants of a supernova. And a supernova is obviously when a massive star has grown and run out of oxygen and exploded. And it's in the heart of this that all the heavy elements, heavier than iron, were formed. This is how to link to the alchemy metaphor. This is where gold is made. So the old alchemists who were trying to convert, the base metals into the more pure elements like gold, it's not impossible. You just need a supernova. You just need a lot of energy. And I want to jump back into this supernova because in the depths of this space is what makes deep learning work. And I'm going to now jump into the depths of that.
The journey for each of us begins here. We're going to explore the cosmos in a ship of the imagination, unfettered by ordinary limits on speed and size, drawn by the music of cosmic harmonies. It can take us anywhere in space and time. Perfect as a snowflake, organic as a dandelion seed, it will carry us to worlds, dreams, and worlds of facts. Come with me.
So you might have seen this, or Deep Dream. The basic idea, it was some research that Google released last year, or 2 years ago now, actually. And you probably hate Deep Dream by now. It probably lasted like maybe 2 minutes, if you did like it at all. I really love Deep Dream. It's not the aesthetic that I love, but the algorithmic poetry it just blows my mind. I wrote a big blog post about this actually. On one level, so it's a deep convolutional neural network. It's very loosely inspired by our visual cortex in the way that the neurons are connected, so that there's a receptive field and patches look at different parts of the image, so that it learns filters. And lower down in the network, it learns basic things like edges, and as you go higher up, it learns more abstract concepts, like you might learn a nose, it might learn a face, and it learns all of this by itself. And so on what's happening in Deep Dream is basically it's a network that's been pre-trained to classify images. So you give it an image and it says it's a cat, it's a dog, it's an airplane. So it's got loads of neurons that are firing and it's trying to determine. But in this case, what's happening is, instead of looking at the output of the neural network, which is where it says what's actually happening, you look inside and then you amplify it. And then you say, well, how would I need to modify the image to maximize this activation? Which is kind of like saying, what do you think you see? Draw what you think you see. So it's a bit like looking at a cloud and you think you see a face and you say, draw what you think you see. And then you look at that and say, now what do you think you see? And it's this feedback loop. So it's a real perfect example of a confirmation bias. So metaphorically, I quite like that idea. But my favorite aspect of it is, and this is kind of the base of everything I'm into right now, is a lot of people say, oh, it's puppy slugs and bird lizards. But there are no puppy slugs or bird lizards, right? There's just this weird texture that we look at and we say, oh, it kind of looks like a puppy. That's exactly what the network's doing. So what's happening there is part of our brain is going, it kind of looks like puppy-like features, it kind of looks like bird-like features. It's not a bird, it's not a puppy, but that part of our brain is activated. So what's happening is when we show the image to this network, it thinks it sees a kind of puppy, it amplifies it. We look at the image and we think, oh, I think it kind of looks like a puppy. So there's this duet happening between us and the system in recognizing and, crucially, projecting meaning onto noise, which is what machine learning is all about, trying to make meaning out of structured noise. And it's what cognition is. It's what we do on a daily basis. Everything that I'm saying means nothing to the universe. It's just pseudo-random fluctuations in air pressure. But when it enters your brain, you project meaning back onto it. And machine learning is a way of turning this into this, after which we look at and we complete the picture. So I want to talk about a project that was very much inspired by this. It was commissioned earlier this year. I showed it at Stripe. It's a VR project. And there's a few motivations behind this work. One is what we perceive to be real, what we see, is a reconstruction in our minds. It's a simplified model of the world, limited by our biology and physiology. Perception, including vision, is an active process. It requires action and integration. The actions that we take affects the reality and the meaning that we construct in our mind. And perhaps most importantly, even when presented with the exact same information, the same images, everybody will experience and will see something unique and personal, which nobody else can see or even understand. And I'm interested in these ideas both on a very low level, on a perceptual, cognitive level, but also on a higher level, especially now with the kind of political polarization that we're seeing and our inability to perhaps empathize with those that we don't agree with. So it's a VR piece that explores the concept called binocular rivalry that I'm going to talk about in a minute. So a few kind of motivations. This is an Australian jewel beetle. I don't know if you know this story. It lives in Australia, and the male looks for a few qualities in a female. She's got to be brown, got to have dimples, and the bigger the better. And then man comes along, it is man, and throws their beer bottles out in the outback. And these beer bottles are brown, they're dimply, and they're big. And this bug almost went extinct because they prefer to mate with the beer bottle than the females. And the beer company had to change the bottle. So the point of this is that this bug has a very simple model of the world. It's worked for it for millions of years. It doesn't need to know more. It just needs to know who it should mate. That's how it's evolved. Another example that I like is from the German neurophysiologist Jörg Peter Hewitt. He studied toads. He did lots of really gruesome experiments with them. The basic idea is that a toad has a very simple stimulus-response chain. If a stimulus is thin and long and moves in the direction of its axis, it's prey. It'll attack. If it moves sideways, it doesn't attack. And through some really gruesome experiments, they found out that this filtering happens in the eyes. The rest of the brain doesn't even know about the rest of the vision. The eyes, the way the retinal ganglion cells are wired, determines whether it's prey or not. And then the brain just decides whether to attack or not. And why do I talk about such lowly animals? Well, if you subscribe to the notion that man was created by God in his image, then it's irrelevant. But if, like me, you believe that we are the results of a natural process of evolution and basically random mutations and descent by modification by descent, then we are just a little bit further down this chain. We are by no means the apex of creation. So it's important to remember that everything we see, as real as it is, as it feels, we might be just like a toad or the Australian jewel beetle. And there's plenty of kind of perceptual hacks to back this up. Another kind of driving force was our eyes are often likened to cameras, as if light falls on the retina, forms an image, and that's how we see. But actually, that's not how seeing works. And in the olden days, it was thought that we actually shot rays out of our eyes, and that's how we saw. I'm going to skip this a little bit because I'm probably going to be a bit late. But that extramission theory, it was called, it captures one aspect which I really like, and that is that seeing is an active process. Basically, the bit of the eye that's actually high resolution is tiny. It's about the size of a thumbnail or two when you hold your hand out. The rest of it is, this bit's really low res and mostly not color. But we look around, we saccade, as it's called, and that's how we construct the image. And there were lots of experiments in the 60s by Alfred Yarbus. He also found that the way we look around the scene affects how we extract the meaning. If you ask someone to a question like, how old are the people, what's happening, etc., the way they scan the world is different. So this VR piece, it uses a thing called binocular rivalry, which is when two eyes are presented very, very different images, which doesn't really happen in real life usually. Quite crazily, what happens is, if the left eye sees that, right eye sees that, your visual experience is a mixture. And this is not like a visual experience of when you close your eyes and you imagine. You literally see something like this, and it changes, it moves, even though the stimulus is static. And this is different for everybody. I have no idea what you experience when you experience this work. So it's called Fight. I'm going to show a tiny snippet. It's completely pointless, but just to give you an idea, this is the kind of thing that you'll see in VR. So forget about depth perception. There is no depth perception here. You have really no idea what's going on. And what, my experience is sometimes you see little bits of this side, little bits of that side, and they're moving around, and I have no idea what you experience. And most people, I had a feedback forum, most people's response was they just couldn't believe, because like I said, it's not like imagining. Your actual visual experience is changing. So this is how humans, this is an exploration of seeing in humans. I want to get back to machines. How do machines see? Sorry to bring another Terminator reference, but this is not how machines see. This is how people add debug screens to machines' output so that humans can make sense of what a machine might be thinking. But most critically, I'm interested in what it means to be learning to see. So I'm going to actually come out of this presentation now and run some live demos. This is all really, really recent. I've posted a few things on Twitter, so you might have seen some of this, but a lot of it's brand new. Like I was up all night, logged into my server at home, downloading new models, so it's going to be an experiment. Okay, let's see. So the first thing, learning to see, modeling a child's mind, not an adult's mind. So what's going on? This is a neural network that hasn't been trained on anything. And it's training in real time. So what does that mean? What's it training on? So it's basically seeing an image and it's trying to make sense of that image. It's trying to break it down into its components and then reconstruct it. Because if it can compress it, that's kind of a way of understanding it. It runs quite slow on my laptop. So the second image on the left is the output of the image, and the image on the very left is the camera feed. So because I keep moving, I'm going to stay stationary for a while. In fact, I'll point it to you guys, that way I can see. So the interesting thing here, well, for me, a lot of things I find really fascinating, it's going to try and learn this particular scene, but that might be not learning, that's more memorizing. So then the real test is if I move it to another scene which has similar components, is it able to generalize? So the resolution's a bit low, so it's slowly starting to become a bit more clear. But if I move it a little bit, it's completely lost. But it's going to start reforming again. And I can also play with a lot of parameters like the momentum and all that kind of stuff if you're interested in the deep learning stuff. But this is, like I said, this is actually beyond a baby, because a baby is born with all the, well, not all, but a lot of neural wiring intact. So evolution has given a baby an infrastructure to work with. In this particular case, it is just completely vanilla. And there you can see it's becoming a bit more clear. But if I move it, again, it's going to lose. So there's ways of countering this. I can give it a bit of short-term memory, etc. But I want to go on to a few other things. So what if we start with a model that's already been trained on something? So I scraped the art collections of 150 art collections from the Google Art Project and trained a neural network on basically hundreds of thousands of paintings. And it trained for quite a while, and then I said, okay, generate, what have you learned? And so this is some of the stuff that it's generated. And this isn't memorized, so the data set is gigabytes. This is just a couple of hundred megs, the weights in the neurons. So it's kind of learned, it's learned something. I don't know what it's learned really, but they kind of look like paintings. This is what happens when you have a dirty data set. This is basically Donald Trump, Theresa May, Nigel Farage, and Recep Tayyip Erdogan. I'm from Turkey. So I trained it on them, and it's created this weird, I really like this one here. I don't know what the hell's going on there. But again, the process of learning is, I find really interesting. So the video I showed before was that. I'll show another one. Oh no, this is the one I played. So this is a long video. I'm going to skip through. So this is what's happening is there's a neural network. It knows nothing. It's looking at a couple of images, and then I'm like, what do you know? This is not a metaphor. It is literally the world view, in that in the depths of this neural network, there's a latent space, a representation, and all that representation is capable of is producing things like this, which starts out as noise. And I'm just jumping through the video. And so it's constantly looking at a few images. What have I learned about the world? And this is trained on, I scraped astronomy picture of the day from NASA. So this, oh no, wait, this is the art one. This is the art one. The one before I showed was the astronomy picture of the day. So this is, again, starting to learn. There's pencil sketches, there's portraits, things like that. So the next step, I'm wrapping up now, this is the last thing to show, is what happens if I make these networks look at me? What does that even mean? It's been trained on something, it has a world view, then it looks at something that it hasn't been trained on, and it's trying to make sense of it in terms of what it already knows, which is what we do, which is how we make meaning. So. Very flattering camera angle there. So, how shall I do this? Oh, you can't see anything, sorry. So on the left is the live camera feed. On the right is it's constructing an image, and this has been trained on 150 art collections. Now, some of you might know of something called style transfer. This is not style transfer. Style transfer is transferring the style from one image, like a painting, onto a photo. Here, it is constructing an image from scratch based on its world view. And there's a lot of parameters I can kind of tweak. So it's not a faithful representation, but this is basically all that this network knows. This is all that it's seen. So if we ask it, what are you seeing? This is what it thinks it's seeing. But I want to show one last model, which is kind of my favorite. And this model I literally got a few hours ago. It's been training at home. So here, this was trained on, I scraped the Hubble telescope website. So this is not like a stock picture of a universe or a nebula, whatever, with a kind of color applied. because I can, for example, tell it to go dark, and it's mainly stars and like distant galaxies. So it's trained on like the Hubble Deep Field images, things like that. But then as I go brighter, it starts adding in. I mean, the resolution is pretty shit, but yeah, it's running on a laptop. So it's learned about clouds and nebulas, and for example, if I tell it to invert, I don't know, show it something. So let's see what you guys look like. Oh yeah, that's my laptop. So this is really, really early R&D, like I said, and that's really the end of my talk. Just remember, we're all made of star stuff, and thank you. I'll leave the music.
Yeah, leave the music.
Yeah.
It's nice. I like it. Thanks, thanks. Does anyone have any questions? Yep. We have one over there. Yep. Yep. I didn't see. The man with the glasses.
Can you maybe explain us a bit briefly how do you train these data sets?
I can't see you, but
Here.
yeah, so let me quickly. So I'm using a thing called a generative adversarial network, in particular deep convolutional generative adversarial network. And the basic idea of these GANs, as they're called, it starts with a high dimensional but lower than the dimensions of an image, like so maybe like in this case 128 dimensional space, and it learns to produce images that there's another network which is called the discriminator. The discriminator has access to the real world. The discriminator sees what's happening in the world. The generator doesn't. And so the generator tries to generate images, and the discriminator looks at real images and tells the generator whether it's succeeded in fooling it or not. And so there's this rivalry where both networks learn at the same time. The generator learns about the world through the discriminator's feedback. So in this particular case, I'm basically training the networks on loads of images with also a kind of a very processed version of that image. And then later, when I feed the webcam input into it, the network is conditioned on generating an input, generating an output that's similar to the input. So this was kind of codenamed Pix2Pix. If you Google Pix2Pix, you'll find information on it. Actually, so an early version of this I did release as open source, so that the training is not my code anyway. The kind of mapping bit is, and an early version of it I did release with a different model. It didn't have as good results. I mean, this is all very new. I hope that was clear to some degree. I haven't slept much either, so I don't know what I'm saying.
Any other questions? There's one at the very back and one over here and one over here. You win because you're in front.
Sorry. What development in AI that are still emergent and you cannot use yet, maybe, if there are any, are you most excited about?
So I haven't done a lot of reinforcement learning, which is going to be very important. So reinforcement learning is basically delayed rewards. So in this case, when I'm training, it's supervised. You're telling it, this is the right answer, this is the wrong answer, and that's how it learns. Reinforcement learning, which is a lot more kind of potential for the future for interesting things, there's delayed rewards. It's a bit like supervised learning is you tell a kid, okay, that's a cat, that's a dog, and the kid learns. And then, but if the kid goes and kicks the dog and the dog bites it, you say, okay, that's reinforcement learning. You made an action and the environment gave you a kind of reward. In that case, it's an instantaneous signal, so you can learn easily, but sometimes you might take an action and then months later you get a reward, a signal, and you have to figure out why that happened. So I'm very keen on that. But really, the big thing is one of the big open questions in AI is kind of intrinsic motivation, or like what's the cost function. It's all right designing and studying algorithms, but you have to specify what you want to, what's the objective. So in these cases, like the reason why this Cosmos thing kind of works a bit is because of the objective that I defined. In the previous version, it didn't work as well because my objective wasn't very good. So we all have an intrinsic motivation that puts us out there in the world to learn. And there's a lot of research into what is the ultimate intrinsic motivator. And that's a very interesting area of study. I mean, it's more philosophical than anything, but tested through computational models.
Great, thanks. I think we should wrap it here. So join me in thanking Memo for his presentation.
Thank you.
So I'm going to trot out that cliched moderator's line and say it's been a very full 2 days with lots of ground covered, but in this case I think it's actually quite true. We've looked at an enormous amount of material. I think we've zeroed in on a few key issues, things like learning, but also the black boxing of our technology and how things scale up and down, our senses and how that differentiates from sensors and what they can tell us, Rumsfeld's known unknowns, which came up a few times, and ultimately I think the whole 2 days really looked at the pursuit of knowledge and what we do know and how we can know what we know. So yeah, that was really kind of, you can't get much bigger than that. But the whole thing as well, and one thing that bubbled underneath that I thought was really important was the ethics of what we're doing and what we're building and why we're pursuing what we're pursuing. I'm especially grateful that in this final panel today, we came up with some thoughts of thinking, well, why do we want to make it the homunculus? Why build that, and what are the motivations for that? So to examine our intentions and our motives as we are ever creative beings, as we can see by all of the artworks as well that we saw today. So go forth with intention, goodwill towards all beings, as we would say at the end of a yoga class almost. So thank you to all of our speakers and presenters and the artists in the show and everyone making the thing work behind the scenes. I'm going to hand this over now to Jarl to really close up our day. So thank you.